So good evening everyone. Am I audible to you all?
Yes, ma'am.
Yeah. So I think we can start today's session at 7:05. So I think that's about it. I think we need to move right there. So let us start anyway. So welcome to the live tutorial session on fundamentals of electronic device fabrication. This is the last week of course details discussion. So we might be having a revision session. So far it has not been intimated yet. So but if there is an option for an additional session, surely I'll be taking the additional session. So by the way, when is the exam scheduled?
21st September, I think.
21st. 21st means coming Wednesday, right?
No, no, September.
September, fine. So, then there is plenty of time. Then probably there will be an option for a revision session. Not now, maybe towards 21st September, just 1 week before or that, you might be getting a mail regarding the revision session. Yeah. So, and from the first week assignment, like according to the textbook and the notes that I've gone through, it says that, where is it? Yeah. The final step is testing. First is like we had been discussing in last class. First is material preparation. Then second is crystal wafer preparation. And the textbook I have requested, I've not got it yet. Once I get it, I'll be mailing it to you guys. Then next is fab, salt, and yield. Fab, salt, and yield. Then comes packaging, and finally it comes testing. So this is the way in which it is given in the textbook, like the difference in what was taught in class and what was given in the assignment, that has been intimated to the TA. Then they'll inform to the professor, and if there is a requirement, there will be action taken against that. So I hope it's clear. So according to the textbook, last stage is testing, that is final electrical testing will be the last stage. So material preparation, basically conversion of sand to polycrystalline silicon. Then crystal growth and wafer preparation, single crystal ingot is converted to wafer. Then we have sorting the good chips inside the fabricated wafer. Then finally connecting the chip to the electronic device and providing proper encapsulation, and all that comes in packaging. And finally electrical testing before shipping to the customer. And one probability is that this is the testing of the final IC. You might have confused it with testing of the chip. Testing of the chip actually comes in wafer fab salt and yield. Maybe that might be the reason for confusion. I'm not sure. Finally, the IC will be tested at the last step. In overall manufacturing process, testing is the last step. But here in fabrication salt and yield also, what happens, the good chips will be sorted, and good chips will be sorted based on different kinds of testing that we discussed in last class, right? Thickness, then conductivity, resistance, all that will be measured, and then we will be doing the fabrication sort and yield. So that might be a reason why there was a confusion. So I hope it's clear now. Yeah. So is it clear now?
Yes, ma'am.
So I think with that we can move on to today's content. See, last week contents are quite elaborate, so I'll be trying to touch up on most of the things. So let us see anyway. So first comes process evaluation. So what is meant by process evaluation? Can anybody recollect from what they learned in the videos?
Ma'am, there is many stations processes in the wafer manufacturing.
Yeah,
Then we have to evaluate each and every steps.
yeah. So basically, process evaluation means that whatever process and device evaluation, what it is used, fabrication goals, fab goals should be met, which means that every device, whatever you have prepared, like whatever you have manufactured, will be having, whatever you manufactured will be having something known as process window. Process window. Basically, what it means is that it is the maximum level for defect density, and the range, for example, in case of an IC, it is the maximum level of defect density. Defect density maximum. So for example, once you have manufactured your IC, everything is set, you prescribe a range from say X to Y. This is the window in which the defective density should lie. Anything greater than y will be rejected. So that is the process window. And one more criteria is the thickness. For example, you have grown an oxide layer, you have deposited an oxide layer, so and so. And there also we define a process window, that is a thickness value from x to y. And if the thickness is not lying in this x to y range, what we will do, we will reject the particular wafer. So that is what is done in the process evaluation process. So everywhere for resistance, conductivity, thickness, etc., etc., we will define a range of values within which the manufactured IC should lie. Anything greater than that will be rejected. So for measuring this, there are three major parameters, that is three major yield measuring parameters. These are known as yield measuring parameters. There are basically three important yield measuring parameters. Does anybody remember what were these three? The three were discussed in class. Yeah.
Fab yield, sort yield, packaging yield.
Yeah. So first one is fab yield. Then we have something known as salt yield. And thirdly, we have something known as packaging yield. Fab yield basically means ratio of total number of wafers that came out of the fabrication process to the total number of wafers that were started in the fabrication process. So initially, like if you have the numerator and denominator, the denominator will have the total number of wafers that were sent in for fabrication, and finally after like removing the defective ones, how many came out of the fabrication process will come in the numerator. Basically, wafer, this will basically be wafers out of fab by wafers started in fab. So that is fab yield. Then we have salt yield. Salt is basically is the number of functioning dies to the total number of dies. So in wafer we had divided it, right? So each of these units or each of these functional units were known as dies there, right? So in salt yield what we have is functioning dies, that is good ones. Functioning dies on the wafer divided by total number of dies on the wafer. Even if there are say hundreds of die in this one, usable ones will be something like 95 or 98. So that ratio will give you the sort yield. And finally you have the packaging yield. Even after all this, there is one more set of testing, and in packaging yield, it gives the ratio of total number of packaged dies which pass final electrical testing to the number of good dies started for packaging. So basically, packaging, passing, final testing, final electrical testing divided by good dies at starting. Good dies at starting of packaging. So basically using the name itself, you can remember this packaging yield basically it defines the start and end of the packaging process. Say n number of good dies were sent in for packaging, but after electrical testing, only an X number of dies came out. So that is the packaging yield. So these three are important parameters. You can expect questions from this part.
But
I hope so.
yes,
Yeah. Yeah, tell
then
me.
in packaging yield,
Huh?
in numerator, packaging die that passes the electrical test. Okay, ma'am.
Yes, yes.
It means testing is done before packaging.
See, that is what, even after all of this, final IC will be tested, right? Initially in IC manufacturing, that testing refers to the final product. This part comes in fab and salt part.
Okay.
Yeah, this whatever testing we are talking about will come in this step. After that, it will again there will be another set of final testing. Yeah, I think that is what was the reason for your confusion. It will be clarified soon, I hope. I have sent a mail to sir and the TA, so I hope he confirms soon.
Okay, ma'am. Okay, ma'am. Understood. In general statement, packaging is first, then in last
Yes,
stage, testing.
yes,
In general term.
in general. But in fabrication, sort and yield itself, there will be many processes.
Yes, ma'am.
Testing
Within
this,
the process, there are many minor testing we can.
yeah,
But final in general statement, packaging is before the testing.
testing part, yes. Then what was discussed? Then something known as what is meant by a station? Can anybody tell me what is a station?
Station means every steps and process like for lithography is a station, masking is station, patterning.
Yeah. So in station, like we are connected to station, there is something known as the station yield also. This is another parameter. Station yield basically gives number of wafers leaving station divided by number of wafers entering the station. Yeah, this is the difference. Number of wafers leaving the station by number of wafers entering the station. That is the station yield. So, and one more thing that you have remembered in this context is there is something known as fabrication yield. Fabrication yield can also be calculated as station yield 1 into station yield 2 into station yield 3 and so on. So here we have got fabrication yield as fabrication out of each fabrication step by wafer started in that fabrication step. One another way of finding it, we have to multiply all the station yield. Suppose there are some n number of station yield 1 till station yield n will also give you the fabrication yield. This is another method for finding. Is it clear?
Yes, ma'am.
Yeah. And then let me check the summary. What all were there in that. So there is these three types, then fabrication yield water. So what are the factors affecting fabrication yield?
Number of processing steps
Yeah,
and
wafer breakage and warping, then process
chemical,
variation, process defects,
chemical.
yeah, and mask defects, all these things. So number of steps. So basically as the number of steps increases, what happens? Individual yield should also increase in order to maintain the overall fabrication yield. That is one thing. Then wafer breakage and warping. So it is related to basically handling of wafers. So if it's there is a mishandling and eventually what happens, there is a bend in the wafer or there is breakage, it will affect the overall output. Then process variations. Process variation is related, like it is related to the process window that I mentioned. Like whatever fabrication process, whatever is being done in the station, it should be done in such a way that the output wafer that we are getting should be aligned inside the process window. That is between the X and Y range of value, pre-specified values. That is process variation. Then we have something known as process defects. So in each stations during processing, there is a possibility that some external defect can be introduced. This also eventually affects the fabrication yield. Then finally, then mask defects. In case of mask defects, instead of defect happening to the wafer, the initial mask itself will be defective. That also will affect the fabrication yield. So these are the steps or the factors affecting fabrication yield. So is that clear?
That's right.
Yeah. Then what is there? So next we have something known as yield model. So yield models will be used and then they will be helping us in predicting the fabrication cost associated. So basically it relates the steps, defect density and size parameters to the wafer salt yield. So there are different models. So based on your class, can you tell me what were the different models discussed in class?
Poisson model, Murphy
Yeah.
model, seed model, uniform model.
Yeah. So we know that defect density is something that affects our fabrication yield, right? So using these yield models, we can predict f of t, that is the defect density as a function of the defects. So basically, let me say, so first one is Poisson's model. So Poisson's model, how would the curve look?
Randomly distributed.
Sorry?
Random distribution of defects.
Yeah. Poisson's model, basically it's the simplest model. It's also known as the exponential model, and it says that consider a wafer with n dies and n defects that are randomly distributed in the wafer. Then probability is given by probability of a defective die is given by exponential of minus m power k divided by k factorial, where m is our small n by capital N, and small n was defects that are ran. These are defects, and capital N is the number of dice. So this is the Poisson's model. That is, it predicts a random distribution. So basically, P of K, it means probability of a given die having K defects. So you should remember this. Suppose there is a problem, you will be asked to find the probability of a given die having so and so number of defects, and they will mention what type of model has to be used. So you should remember that P of K is equal to, suppose it is said that this is a Poisson's model, it should be exponential of minus m power k by k factorial, and where m is small n by capital N, where n gives the number of defects and n gives the number of dies. So is that clear?
Hello,
Yeah.
ma'am. Audio is not coming.
Hello. Hello.
Yes, ma'am.
Yeah. Until where was I speaking? Till where were you able to listen?
Just in this slide, ma'am, probability of the given dies having K defects.
Huh. So basically, there could be problems from the session. They'll ask you to calculate the probability of a given die having K defects, and they'll mention the type of model. So of course, you have to memorize what is the equation for a given model and what are the variables inside it. For example, if it said that it is Poisson's model, P of K basically means probability of given die having K defects, and it is given by exponential of minus m power k by k factorial, which means that we can get the probability. And here you should also remember m is given by n by capital N, which means defects by the number of dies. So is that clear?
Yes, ma'am.
Yeah. So that is there. So next one is Murphy's yield model, right? Murphy's yield model, was it discussed in class? I don't think so, right? Poisson's uniform triangular and seeds model was discussed, right? I think Murphy was not discussed in
Actually,
class.
ma'am, just sir retained the formula and told that this is the triangular.
Okay, that's all. So then there may then probability is that there won't be like numerical questions from this section. So and one good thing to remember is you can like memorize the plots how they look. So can you tell me how like Poisson's distribution will look?
Vertical line.
Yeah, it will be a vertical line, and that vertical line will be marked by D0. This is D, and this is F of A. Yeah. So defect distribution, f of d is the defect distribution function and d is the defect density. Is that clear? And what is d0? Can anybody tell me?
D0.
Yeah.
It is a constant. Chip defect density.
Yes, exactly. Chip defect density. D0 is chip defect density. So please try to remember what these variables are, because in problems and all they'll just mention they'll say a distribution function, they will say defective density, they will say chip defective density. So based on this terminology you have to identify what is given to you. If they are telling just a defective density, it means d value. If they are saying defective distribution function, it means f of d. And if they are telling chip defective density, it means d0. So is that clear? So try to memorize like what the terminology is. So in uniform distribution, this will be the case. And this, suppose this is D0, it will be such that this is 2 times D0 and this is half of D0. So this is the case in uniform distribution. Uniform distribution, this is Poisson's distribution. Yeah. In triangular, the same thing goes. The curve would look like, suppose this is f of d and this is d, and somewhere you have d0. The center of the triangle will become d0, and from there you have something like this, and the height of the triangle will be 1 by d0. This is the triangular model. And finally we have one more model, that is the seeds model. This is f of d. So it will be having an exponential, and tangent to this will meet the x-axis at d0. So these are the different model. This is the seeds model, and we have, this is the triangular model. So like that, there will be different distribution functions. Basically, it helps us in predicting. Suppose you have n number of chips in a wafer, you can basically predict what will be the number of defects. So this thing here we discussed, right? Probability of a given die having so and so number of defects. That is what basically these function helps us in identifying. So then that is there. Then yeah. So then comes wafer fabrication cost.
And if anyone asks which is related to the exponential,
Yeah.
then answer should be Poisson is exponential and seed model is exponential. Am I right?
Poisson's model, I would say, it means random distribution, I would say.
But in formula there is exponential term e power minus m, like.
Yeah, but if you compare with the equation for, I think there is yield function is given by 1 by 1 plus d0 into a. And a in that case will again be more generalized exponential term. But see, suppose if the question is being asked like which is an exponential, then you would should the answer would be seeds model.
Okay, ma'am.
Yeah. Poisson's model, it helps us in predict. It's assuming that the defects are randomly distributed inside the wafer. That is the case. So next is wafer fabrication cost. So what are the components of wafer fabrication costs?
Actually divided into types: the fixed cost, which is
Yeah.
fixed,
Yeah.
and variable cost, which is depend on the manufacturing, how many wafers you are manufacturing within a time period.
Yeah. So I haven't seen problems being asked, but if at all there are numericals, try to remember this thing. S plus, it is given in your summary PPT. S
In
plus
summary
V
given,
plus Y, sorry,
no, ma'am.
TPT into Y, TPT into U. Basically, it has the fixed cost component, the material, labor, and process cost component, then cost of wafers that are scrapped due to defects, then lifetime of the tool, then wafer throughput, then yield factor. It depends. It also depends. Yield factor we have already discussed, right? How to calculate yield factor. That value. Then total tool utilization factor. Usually they don't ask problems related to this. Max to max, it what is being asked is what are the two categories of costs. That is basically fixed cost and variable cost. Fixed cost which is present regardless whether we are doing a manufacturing operation or not. For example, what it comes in the capital cost that we have already kept for maintaining the unit or for establishing the plant, etc. Then variable cost depends upon the number of output that is produced, how much labor is involved, how many wafers are to be produced, and so on. So that is fixed cost versus variable cost. Then comes clean room designation.
Utilization factor, what does it say?
Sorry?
Utilization factor.
Yeah, tool utilization factor. So basically, tool utilization factor means that, so basically a tool has a lifetime, and suppose you have purchased a tool and the tool remains idle for so and so time. And there is another factor that the tool is in use for so and so time. Based on the ratio, like depending on the time from which it was purchased. So is that cost actually handled well enough? Suppose you are buying it and you are keeping it idle means that the tool is being underutilized, right? Based on that, we will be deciding a factor. That is the tool utilization factor. Yeah. So then what is there? Then clean room designation. So what is basically meant by
The
clean?
previous one you have told.
Sorry, yeah, tell me.
Can you repeat that wafer fab cost?
Wafer fab cost means all these factors. Yeah.
Yes.
Is the summary PPT with you? So it's, I think it will be very lengthy to note down. There is a summary PDF uploaded. So whatever that has been discussed in the previous week, it is given. And there, if you see in page number 5, it is given. Like there is an image as well as whatever is involved in fabrication cost, and each of the explanation for this is also given. So basically it has fixed cost, then material and labor and process cost when the tool is running, then cost of the like wafers that was scrapped because of the presence of defects, then based on lifetime of the tool, then wafer throughput, then the yield factor that we have an equation for, then the tool utilization factor. So these are the different things.
Okay.
Yeah. So clean room designation means that, so they will be given different names. Clean rooms will be having an ISO class like 1, 2, 3, 4, and so and so. Basically, what it tells is that what is the limit of particles or dust or different species that is allowed inside the clean room. If it is ISO 1 means that it will be from what, 10 to 0.083. There will be, let's say, an x to y range which tells us the size of particles that is maximum allowed in the clean room. So based on that, it will be given different designations like ISO 1, 2, 3, and so and so. And if it goes to like something like ISO 6, the particulate size will be in the range of 10 power 6 to 320 microns. That will be case. If it is ISO 1, it will be somewhere in the range of 10 to 0.8083. So this table is also there in your summary PPT. Please go through. Yeah. So this is based on ISO. Similarly, there will be other standards also that are followed in other countries. That is clean room designation. And you have a graph as well, which gives the particle size in microns versus the relative particle concentration. In that you can see a range from class 1 to class 1 lakh, how the graph turns out to be. That is also there. Yeah. Then different types of filters and so and so. Like fourth week, there is a lot of content, and that is discussed in a small time limit, I guess. So there is something known as HEPA filters. Can anybody tell me the full form of HEPA? Something known as HEPA filters in clean rooms.
HEPA filter, ma'am.
Yeah,
But it is used in ball design.
yeah, basically
Ballroom
it is
design.
used to, yeah, in clean rooms it is used in the hoods to minimize contamination. But there is a full form for this HEPA. In the
High
images,
efficiency,
yeah,
high efficiency particle attenuation.
yeah. So basically high efficiency particulate attenuation. That is HEPA filters. So there are few clean room designs given to you. So there, if you carefully see, you can see how a clean room design basically works. It will be having a pre-filter blower. Then in the hood itself, there will be a HEPA filter, and there will be a wafer workstation, and there will be continuous airflow. Basically, what happens is that using a setup, what we do is that we'll minimize the contamination to such a level that these standards, what we mentioned before, are met. So in that itself, there are different designs. There is a laminar design, there is a ballroom design, and in that ballroom design is currently used. So if you have the images with you, you can just see and revise your memory if you have the images.
Ma'am, one question is
Yeah,
there.
yeah, tell me.
Uh, Tunnel bay concept. Sir told the tunnel is the area between bays and
Yeah.
bay is the clean areas.
Sorry, can you come
Actually,
again?
sir told that tunnel bay concept.
Okay.
Tunnel means area between bays
Okay.
and bays means clean areas. Okay, ma'am. Actually, but I'm not visualize what does the structure and how it look
I
like
think it's not
tunnel bay.
like that. It's basically bay or tunnel and region between two bays is chase. This is the thing that I remember. So this is the thing.
Bay chase is clear, ma'am. In
Yeah.
figure it shows, and I understand.
Yeah, yeah.
Okay. Chase means this is contaminated air, and
Yeah.
base means it's clean air
Yeah.
where our favor is kept. Okay,
Yeah.
it is clear.
Yeah.
But if we club together bay and tunnel, then how it differentiate bay and tunnel?
Like bay and tunnel, I think are used interchangeably. Like it's the same thing basically.
No, actually, in lecture, sir told the Uh, Clean room design, one is ballroom design, second is tunnel bay concept, third is bay and chase concept. Then tunnel bay concepts are told that bay is the clean area and
Yeah,
tunnel is area between bay. Means between the bays there is tunnel.
that I'm not able to visualize from this. If you see the image also,
Actually, image is not. I haven't seen any image of
yeah,
this.
when
Okay,
I,
man. I'll search on Google if any.
yeah, like I don't remember that kind of a differentiation. So let me check 1 minute. So
In lecture
initial,
actually so told. In lecture actually so told.
which one? Which lecture do you remember?
Yeah, this is actually I think clean room design and contamination control lecture.
So let me check. At least let me check the textbook. What is being said there?
In that lecture, sir actually written the on board.
Okay. I'm not able to find it now. So let me check. I'll check and get back to you. So basically, what was told is that one is tunnel room design, then we have ballroom, and then we have bay and chase design. Like three are separate was mentioned in class. Is it?
Actually, ma'am, one figure sir also draw which is related to bay and chair concept.
Okay.
But another concept are also told a tunnel bay concept.
Okay. Tunnel
Then
bay
what is the
concept.
difference?
Yeah,
Yes, ma'am. Then what,
that is what I'm not also understanding. Okay, let me check. Can you tell me the different names that he mentioned?
in which one?
Like what were the three designs he mentioned in class?
Yes, yes, yes. In heading clean room design, sir mentioned 3 points. One
Okay.
point is first point is ballroom design.
Okay. First one is ballroom. Okay.
In that, sir written hoods were used for fab HEPA filter.
Okay.
Okay. And second point, sir mentioned tunnel bay concept. Tunnel bay concept. In that, sir told yes. In that, sir told bay is clean area
Huh.
and tunnel is area between bay.
Oh,
Only this is mentioned by sir. And third is bay and chase concept.
bay and chase concept.
This is the ballroom design. And
Yeah,
in
that I agree. Bay and chase is
yes,
basically ballroom design where
yes, and one
chase is
figure,
between the base. That is there.
yes,
But
and one figure also
this
drawn by
part
sir.
I'm not understanding what he meant by saying that. Okay, let me check anyway.
Okay.
Yeah. Then, like next is passive elements versus active elements. Passive elements versus active elements. Can you tell me the difference? Passive elements versus active elements?
Active element possesses the energy source and passive element can consume the energy and modify the energy,
Yeah.
something like that.
So can you tell me once more? I'll write under these headings. Yeah. Just everyone try to attempt and answer so that you need not give an additional session for study. So passive element basically means it. What does it do?
Consume the energy, modify the energy.
Yeah, it modifies. Right. And in active elements, what happens?
Energy source act as the energy source,
It
process the
acts as a
energy.
source. Now, can you give me some examples?
Resistor, capacitor, passive element.
Resistor, capacitor, passive, then
And
active elements,
diode, transistor, op-amp, BJT, FET, JFET,
etc.
MOSFET.
etc. Okay. So there are lots here. MOSFETs, BJT.
Inductor is a passive element. No?
Yeah.
Ma'am, why we are not fabricating inductor and IC?
Inductor as it is not fabricated, but certain regions I believe will be doped to act as a dielectric layer. That is what I remember. That reason I'm not sure why.
Transformer, we are not able to fabricate on wafer.
Yeah.
Transformer. Can we fabricate transformer like structure, something like that? Input coil, output coil, acting like as a transformer in the wafer.
I don't think so. I've never read about that part. Does anybody else in class know whether like a appropriate reason why inductors could not be fabricated in IC? Like possible reasons why? Does anybody
No,
else know?
It may be inductive effects which may affect the
Other
adjacent
components, yeah.
adjacent components
Yeah, that
because
could
there
be
is
a
a
reason, yeah.
electromagnetic field on the inductor. It's maybe reason I think.
Yeah, maybe. I'm not sure. Even I'm not sure.
Yeah.
Then what was there in previous class? Then logic gates and or not, I think everyone knows, right?
Yes.
And then finally packaging and bonding. What are the different types of bonding? Wall bonding, wedge bonding, tape bonding, then flip chip bonding, then different types of packaging, like mostly subjective things. Yeah. So these are the contents for previous week. Does anybody have any doubts from these specific areas?
Yes, ma'am.
Yeah.
And in process water,
In
there is three in process water.
okay.
There are three types of water: normal water, DI water, regular water.
Yeah.
In market, ma'am, we purchase many waters. Okay,
Yeah.
ma'am. Aquafina, like that. This is the normal water.
Normal water basically comes this tap water what we are getting. Whatever we are getting in packaged drinking water is also to some extent it is deionized or demineralized, but the range of values will be different for that what we use in industry for IC fabrication and for drinking. That acceptable like, ion limit will be different for both. Normal water basically means tap water. No, not modified one.
No, ma'am.
Yeah.
Actually, I want to know differentiate between the normal water and regular water. Okay, ma'am.
Okay.
Regular water and normal water. What is the difference?
Regular water, I've not heard the terminology.
Sir actually written the three types of water. Normal water means dissolved minerals and impurities.
Yeah, normal one. Okay. And
Yes, ma'am.
regular what
And
is
in
mentioned?
0.004 mega ohm per centimeter.
Okay, like very less conductivity, regular water. But I have not come across the terminology regular water. Deionized water is there, demineralized water is there, then normal water. Like regular water, I've not come across.
And in
Maybe
market, whatever drinking water available, this is normal water,
that is demineralized water, I believe.
DI water.
No, that is deionized water. If there is difference in that.
This is normal water no, in market.
Normal water basically the ones we take from water bodies directly without any modification ones. There
And
will be
market
impurities, etc., etc., etc.
and in packet market water.
That is not, it is processed somewhat, right? And there is another category called as distilled water that I have heard.
Yes, and distilled water.
Yeah.
Okay.
Deionized means that, as the name suggests, ions will be removed from. Demineralized basically means minerals will be like modified. Like in some cases, like what see some they'll market like some minerals are healthy, they have modified it kind of thing. Then there is distilled water is there. Maybe
Ma'am, is
distilled
there any difference between distilled water and deionized water, ma'am?
distilled water versus deionized water. Let me think. Deionized water. I think deionized is more pure than true. Deionized means completely all ions will be stripped, right? Maybe that too it might depend on the range of like the process window, like the extent of ions allowed in the tube. Yeah, high purity applications they'll usually use in laboratories and all. We used deionized water. You don't use distilled water. That is.
Means purity of
Yeah, purity is the
distilled water
fact
is less.
lesser
Purity
compared
of
to
the distilled
deionized
water.
water. Yeah, the
But
values I don't know.
but ma'am, DI water is the very good for the wafer cleaning. But
Yes, yeah,
in our health purpose, in our drinking purpose, we cannot use
DI
DI
water.
water.
Yes,
I
yes,
think
yes.
it is a pure, but we cannot use because there is no such mineral which can which is used for body. But it is used in the wafer cleaning. That is
Yes,
okay.
yes, but like it won't cause any harm if you drink, but it is not advised.
Yes, ma'am.
Yeah. So
Okay.
basically, distilled water means that it undergoes the distillation process, but then too it is believed that some amount of ions will still remains. But deionized, on the other hand, it's completely stripped of ions. That is what I understand. So deionized will be more purer compared to distilled ones.
Ma'am, in batteries we are using distilled water or deionized water, ma'am.
I think we use distilled water for that. I'm not sure. If there is any corrections, please do correct me. I'm not sure. This is based on my memory alone. I think it's distilled water only. I think like this also will depend upon the amount of cost effectiveness, right? Suppose your batteries are, it's okay to use distilled water in batteries, then why would you go for a higher priced deionized water? In wafer fabrication, at least we need very high, like completely stripped of ions, very high purity water is required. Then you go for deionized water. Suppose your application will work with a lesser like level of purity, then you would obviously go for distilled water, right? From a cost perspective, that is maybe how you can justify that. Like deionized water, if you say it's very costly for laboratories and all, it will be very costly. So supplying that for day-to-day stuff, it would increase the price of everything, right?
Okay.
So I think with that we can start with yeah, yes,
One, I have few questions, ma'am, actually.
yeah, yeah.
In yes, ma'am. In a wafer sort builder, sir told the factor affecting sort area. Okay, ma'am.
Okay,
Factor affecting sort area. Two factor major effects actually: wafer diameter and dia size.
okay,
Sir told that wafer dia if increases,
okay.
wafer dia if increases, then edge dies will decreases.
Wafer dia increases basically
Ma'am,
edge.
actually, if you want, if you can write, ma'am, you can write on board. Actually, I want to some relate other
Okay,
things.
so
Wafer dia if increases,
like 1 minute, let me go to my notes where. Okay, you're talking about wafer sorting, right?
yes, ma'am. Yes, yes.
Wafer
Wafer dia increases, then edge
sort
die decreases.
in. Okay, so what is in this? Dia increases. Okay, diameter
Dia increases,
increases,
edge die decreases,
edge
edge
die.
die decreases. Okay.
Okay,
And another thing, die size increases,
okay, die size
size
increases. Huh?
means area. Okay,
Okay, yeah, die size increases,
means area. Then edge die also decreases.
edge die
Also decreases.
decreases. So basically,
On
if you
behalf of yes, sir. On behalf of this, I told that we go for the larger wafer for more cost effective.
okay, so
Okay.
basically, if
Then
you have some two different types of
Actually, I guess its edge size increases. It's not decreases. If you increase the die size.
yeah, suppose total number of dies in this is say 100 and suppose this is 50. So more number of edge dies will be lesser, right? More numbers would actually be completed, I guess. That might be the thing that he means. Suppose
no,
for same size, on both of this, whatever size we are telling, so this
yes,
same square, if the same square lies here also, then it means that suppose here edge dies are say some 30 out of 100, but here out of 50 some again say 25. If you take the ratio here, the percentage of edge dies is more, right? Like this is like half of it is edge dies, but here only some, like it is comparatively lesser, right? That is what he meant, I guess.
Yes, yes.
Yeah,
ma'am.
yeah.
Actually, in general, actually, if in general wafer fabrication,
Okay,
if we increase the die size,
okay,
then it will in the fixed wafer dia. Wafer diameter
okay,
is fixed. Okay, ma'am, that is fixed.
okay,
Wafer is fixed area, and up now I'm telling about the die size.
okay.
Okay, if we increase the die size,
So this is your one case,
yeah,
and
okay,
here
one case.
it is like this.
Yeah. If we increase the die size, okay.
Okay.
In if you increase the die size, then edge dies will be decreases. Am I right, ma'am? Sir actually written this. Sir actually written this on the
Okay.
lecture. Sir told
As
die
die
size increases, then
area,
edge dies decreases. Is it right, ma'am?
die area increases, yield should decrease. So area would increase means that yield would decrease. Means that edge dies would increase, right? Is it? I don't think that statement is as die area increases, yield will decrease, right?
Yes, ma'am. Area if will increase, then
Yeah.
yield is decreased. It means it is not a desirable condition. Okay, ma'am.
Yes, yeah.
It means area should be minimum.
Area should be minimum. Yeah.
Okay. Okay. It means area should be minimum of chip. Okay. And
Uh,
in other hands are told that die size means die area should increase so that edge die should be less. Means both are the statement is the contradicting to each other. In yield perspective, in yield formula, if you go, then we find that if we increase the chip area, then yield is the minimum.
okay.
Excuse me, sir told when like when die size increases, edge dice also increases. He has told. I think you have written wrong.
Yeah, that's what. Edge dice
Maybe
are more. Yeah.
can you see your notes, what you written, die size increases, then edge die increases or decreases in your notes
Increases,
actually.
increases. We have
Yeah.
written.
So this
You
is
written
correct.
increases. Actually, I written the decreases. I think I written wrong.
Yeah,
Yes,
because
you
area
have.
increases means edge dice decrease. That is why your yield is going down, right? Is it?
No, no. Yeah,
Yeah, it
die
is
size
fine.
increases, then no, die size if you increase, then S die should be decrease or increase.
Increase, I think.
Increase.
Like comparatively, they are telling. Now, previous case also we see in comparison. Na?
Yeah.
Like 100 are there, 30 are there. Here you have higher number of die.
So here, suppose there are 100, here is only 50, right? So out of that, even if some say,
It means
yeah,
it means I think, ma'am, S die should be increased.
yes, edge die should increase as area increases.
But actually in
Percentage.
the
Because I think more than telling edge die, it is percentage edge die. That would be the correct terminology, I think.
yes percentage.
Yeah. So out of this, say some 20 are there, here 30 are there. Here, basically, if you take the percentage is more, right? And here the percentage is less. I think that is what he meant.
Okay, I'll check once again, sir, what actually
Yeah,
written.
can you like other people in class? Can you just compare what you have written?
Yes, that
Yeah, Anil, if you can mention what you have written, can you?
Like die size increases, edge dice also increases. That is actually true.
Okay, die size increases, edge dice increases. Yes, and in diameter also, like as dia increases, edge dice decrease, right?
Ah, yes, ma'am.
And whenever edge dice decrease, there will be an increase in sort yield.
Yes.
Yeah. So is that clear, Manish?
okay, ma'am.
Yeah.
I'll check once again. Okay. Uh, okay. And ma'am, one more thing.
Yeah.
In formula, yield is written y cap in bracket r.
Okay. Where?
Then y
Which
what is
portion? Where?
in general yield model? There is a formula,
Okay.
many
By
formula,
R.
yield formula. YR.
Okay.
Then YR is the yield actually. What is YR?
Wire is the yield integral, right?
R means integer.
Yeah.
Actually,
YR is
terminology
yeah. YR
I want to
stands for
confirm.
yield integral. As such, R means what I do. YR is designated as yield integral.
Int integral.
Yeah.
Int. And ma'am, parallel plate capacitor.
Parallel plate capacity.
In parallel capacitor, ma'am, if you can you show the what sir to draw the figure if you have,
Parallel.
ma'am?
Okay. There is
Sir,
capacitors
actually
are
draw
there.
the
Linear is
in
there.
the
Serpentine is there. Parallel plate. I don't know. Okay. What do you mean? Like what figure? Not sure.
actually, sir, draw a figure in parallel plate capacitor. I want some question on that.
Normal parallel plate capacitor you're asking, or specifically what's R do? I don't know. Like I haven't watched the lectures. I watched it long back, so
Actually, in figure, actually, sir told what figure. Actually, I have doubt on that figure.
You just tell me how the figure looks. We can
Okay, ma'am.
maybe find out.
Just simple draw the. Actually, just simple draw the wafer, ma'am.
Okay, and then
Ma'am, actually, can you draw the?
I'm finding out if there is anywhere. Parallel capacitor. Does anybody else know what the figure looks like?
Like it is a MOS capacitor, ma'am.
Ma'am, actually, I'm telling ma'am, you just draw the on the board.
Okay.
In wave, just simple draw the wafer.
Wafer, okay.
Okay. On wafer, SiO2 layer. Just draw the SiO2 layer. Okay.
SiO2 layer.
Just set the area. Okay.
Okay.
Okay. On top of that, just small area, just denoted the metal on the SiO2 layer.
Okay, small area denoted as metal.
Okay. Just this is the metal. Okay, ma'am.
Okay.
And sir, also draw another metal on SiO2. Just remove the SiO2 layer anywhere.
Okay.
Small area.
Okay,
Just
somewhere
remove.
like here.
No, not here.
Okay.
Other
Okay,
than metal.
here.
Just remove the and fill the metal here.
Okay.
Fill the metal. Fill the metal here.
Yeah, this
Fill
is
the metal.
yeah.
Okay. Okay. Here. Okay. This is the MOS. Actually, sir told the MOS metal oxide semiconductor. Okay.
Okay.
In capacitor, we have two contacts. Okay. Then MOS means metal oxide semiconductor.
Metal oxide semiconductor. Yes.
Then one contact is on the metal.
This part, this will act as one contact, and
It
the
is the one.
contact, yeah, another contact will be this one.
Then ma'am, it is the metal, then oxide layer, then metal. It means metal ox metal. It's maybe called metal ox metal.
Oh, you are asking. Okay, see, think of the view you are seeing.
Yes.
You are
Then
just looking at it from the side, right? But how
yes,
does actually current flow inside this thing? It's not like your like current will go from like it will follow a path from here, here, and it will reach here. So this metal contact is actually in contact with your semiconductor layer, right? This is your SC.
actually, okay. In 3D view, that is okay.
Huh.
You are telling in 3D.
Yeah,
If
this
we are
is just a
considering,
schematic for representing this thing, like just to show that
okay,
so and so layers are there in that.
understand.
Yeah.
And I'm telling also in 3-dimensional aspect. If you visualize in 3-dimensional, then also I think there should be a draw the trench between both metal. In trench there, I have to adopt very high resistivity so that no any electron can be flow.
Yeah, there should
between.
be a high like depth trench should be there. That is true.
Yes, ma'am.
Yeah, that
I
is
think
there.
that is the proper image in
So
3 dimension.
yeah, in 3 dimension. So what we usually do
Like
is that
otherwise there is a leakage current.
yeah, what we do
Otherwise
is
there
that
is a
we'll
leakage
draw this figure plus a second figure along with that trench and those layer we will be drawing.
high
Something
resistivity
like this.
material.
Yeah, that will be there. Yeah, that's true.
Okay. And when in dye separation,
Dye separation.
dye separations are told two types: sighing and scribing.
Okay, dye separation.
Dye separation means dye cutting on the wafer.
Okay.
Different types. There is scribing and sighing.
Sign, what?
SAWING, ma'am, sir told.
Okay.
Why written two terms, ma'am? Sawing and scribing. Scribing, I understand there is a line between the dyes.
Yeah,
We
scribe
simply
lines are there. That is there.
we simply cut the dyes.
Okay.
But there is also a term sighing.
Can you say the spelling?
SAWING.
SAWING. Sawing.
Yes.
Okay, so you are
Sir
asking.
told that sir told that this both are the diamond saw or the scribe.
These both are?
These both are diamond saw or scribe.
I'm not understanding. Like cutting wafers, it can be sawing, scribing, like laser cutting is there, then mechanical sawing. Basically, use a saw, like wood saw, right? Similar to that, there will be a saw, and using that saw, you will cut. One thing is laser cutting. Using a laser beam, you can cut. Another thing, using a diamond, like according to your wafer material, you use a pen like scriber, you mark the edges and then cut. That is there. Scribe, after scribing, you have to break it in opposite direction, just like we cut glass in laboratory. No, same way you can cut a wafer. So these are the different methods of cutting.
And when sealing of the wafer in packaging,
Yeah,
I have to seal the wafer. Okay.
yeah, that is there.
In sealing, we have the two types of sealing: hermetic and non-hermetic.
Yes,
Okay. And hermetic means this is the airtight.
yes,
No any air can be introduced in the sealing area. Okay.
yes,
And in non-hermetic means air can be entered.
yeah.
Then why we go for the non-hermetic?
Like
I always prefer no air
hermetic
should be
ones. Okay, so you're asking why is a need for
yeah.
non-hermetic process?
In which condition we packaged any cheap non-hermetic? Why we go for non-hermetic?
Non-hermetic ship.
Because
Let
oxygen, if you oxygen enter in the cheap area, then it will be
yeah, there will be
react
issues of oxidizing.
react
Yeah,
and SiO2 layer will be
yeah,
formed.
formed. Yeah. Right.
Then why we are studied two types of sealing, hermetic and non-hermetic?
That I have no idea. Like, why would you want that? No, I don't know why that. Like, I understand the difference, but what is a scenario where we use non-hermetic
Yes.
packaging? I'm not able
In
to
which yes.
think of now. There might be, but I think eventually all dyes will be hermetically
No,
sealed. But during
it can
intermediate process, suppose you want to grow an additional oxide layer, you'll have to let some amount of air inside, right? So that is there. But eventually, all like wafers will be hermetically sealed, is what I remember. I don't know specific.
it,
Yeah,
it can be, ma'am, if there is no proper precise material and chip required, then we go for non-hermetic for the cost cutting. And in scientific research, in
yeah. That it's like
spacecraft,
yeah. Depending on
spacecraft,
your applications, you can
absolutely,
maybe
yes.
use. Yeah.
Yes, I think it can be non-hermetic because where cost is, we
But
want
still,
less cost.
then with time, because of the formation of your oxide layer, if there will be a lapse in performance, right?
We can manage. I
Yeah, if
think,
that is okay, means maybe you can use a non-hermetic, less costlier
but
seal.
in
Yeah.
spacecraft where the
We
lots of
cannot allow for that. That is
lots
true.
of amount of invested by government where we cannot deviate. And I think there should be hermetic.
Sealing should be
I
used.
I think this
Yeah,
may be
that could be the case.
okay.
Yeah. Anything
Okay.
else?
No, ma'am.
In that case, I think we can start with today's question answer session, right? So let me load the question answer session. Okay, so I'll do one thing instead of writing, I'll project it here, I think. Because I'm having some issue. Project it here.
Intel, IBM, and Samsung.
Huh?
Well, these are companies uh, uh, manufacturing the any IC from the design level to manufacturing, means design perspective and manufacturing perspective, both is done by this company. Are
That
this company
that I'm not sure. Like to what extent and to what edge of processing they'll do, I'm not sure. If anybody working from industry, if you know better, you can correct him. That
Actually,
type.
ma'am, in no, no, actually ma'am, was okay, ma'am. Actually, in lectures are also told the integrated device manufacturer and fabless semiconductor company.
Okay.
In that, sir told the what example Intel, IBM, Samsung is the integrated device manufacturer,
Okay.
and
So
fabless semiconductor companies AMD, Qualcomm,
quantum, yes, that is there. Yeah,
and in,
lecture part of you okay, but other than that, further details like currently what is the stage? I'm not sure. Like you'll have to check online which company processes what kind of ICs and all those things.
okay. And ma'am,
So
in general, if in general term, if anyone told these companies are the foundries, means foundry, what can I understand the foundry term? Means this is the company which is manufactured or
Yes,
designed
yes.
the manufacturer, I think.
They have fab.
they make these things.
No, no, suppose company A and company B. Okay, company A is only manufactured.
Okay.
This is not any design, any IC, just only manufactured.
Okay,
Means A
based on
is the
someone's
foundry.
design, they are manufacturing. You're asking.
Yes, yes. You, for
Means,
example,
means
Global Foundries is there. They will just take a contract and
Manufacture.
manufacture.
They don't have a
means
design of their own.
it means A company is the foundry company.
Yes, yes.
Yeah. So first question, can you tell me the answer? The process in which electrical leads are deposited on a
I'm
thin
not
film.
visible any, not visible in this case.
Sorry,
Actually, screen is not visible here. Now is visible.
it's not visible.
Now okay, ma'am. Now okay.
Is it visible now?
Now okay, ma'am.
Yeah. So can you go through the question? The process in which electrical leads are deposited on a thin film and then stamped before bonding with the chip is called what?
Tab bonding.
Tap bonding. So what about others? Are you having the same opinion?
Yes, ma'am.
Yeah. Tape bonding. So what are the other types of bonding? Can you tell me?
Ma'am, in wire bonding there is a capillary system, and
Yes.
there is a thermocompression used for pressing the metals on the wafer.
Yeah.
And in flip chip bonding, there is a bump. We refloat solder on the chip, and thus just flip the chip and kept on the package side and pressed.
Press. Yes. Okay. So in
And
tape,
that's
yeah.
the
So these are the explanation for all of this. So basically in tape bonding, the lead system is deposited on a flexible tape by sputtering or thermal evaporation. And then it is combined with patterning or stamping to make the leads. And in wire bonding, as you said, there will be a capillary and a gold wire will be fed and using thermomechanical compression, it will be bonded with the die and the lead. In wedged bonding, so basically it uses ultrasonic vibration and the capillary through which the metal is fed will be ultrasonically agitated to form the wedge bud. And finally, in flip chip, wires are replaced by a solder pump will be used and these bumps will be deposited on top of the die and the chip will be flipped and bonded with the packaging using the solder pumps. So these are the different bonding processes. So in final like video it was mentioned I guess. So are all processes clear?
how tape is working. Actually, I'm not visualize the scenario. Flexible tape by sputtering and thermal. How tape is look like, how it's working,
Like
what
I
is the meaning of
think
tape.
there will be an image, I guess. Let me check for the image I can. Let me check for tape bonding image.
Tape means this is a wired mesh type tape or a simple taping.
It is like it's flexible in nature, and when you apply pressure to it, based on that, it will bend and form the lead. That is the case.
Okay. It
So there
means
will be a
whatever
yeah. Tell me.
means metal particles are already deposited in the
Yes,
tape, and
yes.
tape is just kept on the wafer.
Patterned, yeah. And it will
Just press.
stamp. Yes, we'll stamp it with
Okay,
a particular
pressed.
amount of force, and then it becomes bonded.
Okay.
And for stamping, we use something known as a thermod.
Remote.
And since it is flexible and it has electron like conducting particles on it, the tape will take the shape like what you want because of that stamping process. Yeah. Okay. So as fabrication goals have to be met at individual process levels are referred to as individual process level. So please you check and tell. Fabrication yield, process window, process yield, wafer, salt yield.
Process window.
Any other answers? Anybody else? Any other answers? If not, yeah. So basically, in process and device evaluation, there will be a prescribed level that is allowable, whether it is thickness or whether it is defect concentration and so on. So there will be an X to Y range, and anything above that range will be considered as defective. So I hope that's clear. We discussed it in the initial part of this class. So next is an individual step in IC manufacturing process is called what?
Station.
Station. Yes, it's very direct. A term used to describe a cluster of defects on a wafer is dash.
Decoration.
Any other answers? Anybody else? Yeah. Next is the yield model, which uses exponential function for defect density is called
Seed model.
yes. So as the area, what we have discussed, as the area on a wafer increases, which of the following statement holds true? Defect density remains the same, wafer dia increases, wafer salt yield decreases, probability for device failure increases exponentially. And in such cases, in sometimes more than one option might be correct, you have to choose the most apt answer. And if you choose either answer, you will get marks also.
Salt will be decreasing.
Decreasing, yes. Now I think your doubt is cleared, right? Yeah.
Okay.
So this is the case. This is the thing I was mentioning before. So out of the total number you have to see. See here there is 10 good ones, 18 bad ones. So based on that you will calculate the yield. As the number of dice go on increasing, what happens? The yield goes on increasing, and that also depends on the edge dice. So is that clear?
Size increases. Ma'am, here is edge die is decreasing, I think.
Yeah, edge die
Means
decreases means yield decreases.
means
Yield
I
increases.
think
Yeah, it's inversely proportional.
means die size increases, then edge dice is decreases.
Die size increases, edge die increases. Then only your
No,
wafer.
decreases.
Yeah.
If we increase die size, then edge die will be decreased. I think on this picture, this is the happening.
I think we have cleared that right when we told before.
But in that picture, ma'am,
Picture the count if you take, and out of those you have to also select the good ones versus the bad ones.
okay.
Yeah.
Okay.
Then only you can decide the sort yield. It's not just the actual number, but out of that, the defective ones versus the good ones.
Okay.
Yeah. For process chemicals used in IC industry, which of the following statements holds true? High concentration of sodium for better conductivity, low sodium grade chemicals, high amounts of chlorine for good etching, high amounts of potassium.
Low grade sodium chemical should be used.
So basically, why the reason is that sodium is most common ionic contaminant everywhere. In all chemicals, it will be there. So they are electrically active impurities, and basically it alters whatever the semiconductor's intended performances. So we should always be using low sodium grade chemicals when you are dealing with manufacturing of ICs. Yeah. A logical operation, this is like very simple. A logical operation that gives an output of off when both inputs are on is called
And off, off, no,
there might
NAR.
nor.
yeah. So like,
And
and all, not everyone might be knowing and or also need to
only
yeah. Off basically in and
both
means on, then and means it will be ulta. So it will be on. And in case of, yeah, nor in whatever we have the truth table for and nor, you should just reverse it, put it as ulta, you will get NAND and nor output tables. So is that clear?
Clear.
So which of the following statements is false with regards to IC manufacturing? Undoped region cannot act as resistor. In MOS based capacitor, metal can be replaced by heavily doped polysilicon. Many types of resistor designs can be patterned on a wafer. IC fabrication is an assembly line process. Which of the following statement is false? It is asked.
Option A.
Anybody else? Any other options do you find correct? Yeah. So resistors, basically what they do is they control current flow. Every undoped or doped region can be used as resistors. Then many types of resistor designs can be patterned, and the capacitor is a dielectric region between electrodes. Then the simplest one is the MOS structure. Then in IC, it's basically an assembly line process. So that also is clear. So A is the false statement. Okay. Choose the correct statement in case of a BJT. Emitter is moderately doped region, base is heavily doped, the base has least width in the transistor, emitter has a larger width than base and collector.
Option C.
Anybody else?
Because base should be least. Width will be very minimal so that more electron can pass from emitter to collector.
Yeah, exactly. So this is how the width for three regions will look. Emitter will be heavily doped, base will be least doped and small width, and then we have the collector which is moderately doped. Which of the following are both active circuit elements? You have to choose between resistors, diodes, transistors, capacitors, diodes, and resistors, capacitors.
Diode transistor.
A logical operation that gives an output of off when either or both inputs are on is. So basically, it is giving.
No.
Yeah. On, off, on, it is giving. So you have to find out. So it's not. Yeah. So which of the following, yeah, this is just for information's sake. So which of the following is the 4-bit binary representation for decimal 25?
Option D.
Huh?
Option D. No. Actually, 4-bit in 4-bit we have 25. We cannot write.
Yeah. So this thing, if you have to, you can memorize, it would be good. Range of decimal numbers that can be represented using n-bit binary system is 0 to 2n minus 1. Yeah, so 4-bit basically means that 2 power 4 minus 1, that is 15. And decimal 25 hence cannot be represented using 4 bits. 5 bits will be needed for representing 25 in this binary system. That 0 to 2n minus 1, please try to keep in your mind. Yeah. So we'll move to next question. A 10-step fabrication process, this is like problem. A 10-step fabrication process has a cumulative yield of 0.85. Assume that 8 steps of the same station yield, while the last 2 steps are 0.93 and 0.98. What is the yield of these 8 steps? So basically it is telling that total is 0.85. First 8 steps had some X value. Last 2 have some 0.93 and 0.98. So what is the yield of the first 8 steps? That's the question. So please take your time and try to do that.
option A.
Option A. Anybody else? Have you tried? Okay. Yeah, first is correct. So basically what it is telling that 0.85 is equal to some 8. It's for example say x y say n1 n2 n3 n3 etc 8 times into 0.93 plus 0.98. And one more thing they are telling is that all of them have the same station yield. So n1 is equal to n2 is equal to n3 up to n8 all are same. So you just take it as n power 8. So we are asked to find out that x power 8 value. So basically total cumulative yield of 0.85 was told, and then final two steps of 0.93 and 98 is also given. Then there were 8 other stations, but all those stations had the same value. That is why we take x power 8. And finally we calculate the value of x. So we get 0.991. So is it clear?
Ma'am,
Yeah.
ma'am, here actually it's asking single station yield. Okay, ma'am.
Yeah.
There is 8 stations.
Sorry. Yeah. Yeah. Yeah, such type of question, but then the sentence would be framed in a different way. Say, what is the, then they can put the word here cumulative here also, right? Huh, cumulative yield of these 8 steps they can ask, then you should give the answer of for 8 x power 8. Yeah. Okay. Which of the following represents fixed cost in IC fabrication? Yeah. Fairly direct question. Changes in wafer due to various thermal processes is known as warping, thinning, slicing, and scribing. Scribing comes, we recently, scribing and slicing, everything comes part of what? Cutting processes, right? So here they are asking thermal process. Because of temperature difference, what is one issue happening to a wafer? Yeah, it basically bends. Because when it is heated, when it goes undergoes heat treatment, so and so when it is heated and cooled, what happens from high temperature? If there is a sudden variation or if the rate of cooling is not proper, there is a possibility that the wafer will end up bending from the edges. That is warping. It's yeah. Yeah. Huh? Okay. No, annealing is a controlled one. That whatever you told is quenching. Sudden process. Yeah. Quenching, yes. Yeah, controlled one is annealing. No, depends on, suppose in steel, when we study, depends on your, in wafer, it will be annealing, but according to your processes, suppose in steel, sometimes you want something known as martensite, and that case you have to do quenching to get martensite. It will depend on your final requirement. Yeah, it should be, yes, it should be a very controlled process. Yes, yes. Which of the following chip characteristics affects packaging? Note that more than one might be correct. Okay, yeah. Except lithography, everything matters. Yes, tell me. Yeah, sure. Yes, yes. See, but the thing is, here dimensions are given separately, right? If dimensions is not given, then that argument will be right. Like lithography in itself will affect dimension, so that also indirectly affects your packaging. But here dimensions are directly given to you, right? Yeah. So, okay. On a silicon wafer with 2000 chips and 100 randomly distributed defects, what is the probability of a chip having two defects? Use Poisson's model and choose the nearest value. They have given total number of chips and two defects they have given. So, you have to find out. K value is directly given to you. 1.189, you can put as 1.19. Yeah, yeah. So basically, n dice, n defects randomly distributed, it is given. M is given by M by N. So K is given as 2. So here K is also given, and then you have to find M. And M what is given? N by N on a silicon with 2000 chips. So 2000 is your total number of chips, and the number of defects is 100. So basically 100 by 2000 will give you 0.005. And once you get the M value, you can directly substitute in this equation. E power minus 0.05 into 0.05 power, it is given as 2 defects. So K value is 2, and by 2 factorial. That is also, you'll get approximately 1.189 into 10 power minus 3. So nearest value is 1.19 into 10 power minus 3. Yeah. So process water used in clean rooms should have which of these things? Low resistivity, high resistivity. Yeah, high resistivity. That means very low conductivity. Yeah. Process room, this process water is also called as DI water. So basically, see here, normal water contains dissolved minerals, particulates, organics, gases, etc., etc., etc. But purity of DI water used in usually fabrication application is, this is the resistivity, that is mega ohm centimeter. So the dissolved ions will be less than parts per million, 0.03 parts per million or 30 parts per billion. So regular tap water has a resistivity of 0.004. So if you compare the values, you will know the difference. Yeah. So IBM is an example of an IDM. What is an IDM? Yeah. IDMs own and operate own fabrication facilities, as you said before, Intel, IBM, and Samsung. Then fabless semiconductors example include they design the circuit and contract with the merchant AMD, Qualcomm, etc. And foundries like Global 20, Taiwan Semiconductor Manufacturing, and so on. So, yeah, yeah, they don't have. See, foundries they manufacture, they don't have designs of themselves. But these people like AMD and Qualcomm, they have designs, but they don't have the plant. But people like IBM, Intel, and Samsung, they have everything. They have their own designs as well as their own fabrication units. Foundry, basically, what do you call? You call a foundry when it is a manufacturing plant, a big building with all the equipment, the fixed and regular cost. Like they are capable of handling both fixed and regular, all the equipment, the clean room designs, everything. But they don't have the starting design. They have everything ready, but they need a design from outside. Suppose, what do you call? Suppose, yeah, you draw a figure. You suppose you draw a picture and give it to me. I have a printing press. You know how to draw. You have the design, but you don't have the press. You cannot print hundreds of copies. But in my case, I don't know how to draw, but I have a press. You just give me the design. I'll make 1,000 copies. Yes. I have the equipment, I have the raw materials, I have everything, but I don't know how to design. Yeah, yeah. They will suppose if you're talking about Taiwan semiconductor manufacturing and if they are listed as a foundry, it means that they don't design, but they design. Sorry, they don't design, but they can manufacture. But these people, IDMs, what they do is that they design as well as they make themselves. They don't need any external help. They themselves can do the entire process from starting to beginning. So that is the contents for this week. I hope it was clear. And for regarding the textbook, one person had asked me. So I have talked to sir, and once he gets back to me, I'll send it to you surely before examination. Yeah, textbook, e-copy. Yeah, surely I can send it to you also. Yeah, sure, no problem. Yeah, when I get it, I can forward it to like whoever wants it. Just drop an email to me. I'll mail it to you once I get it. Yeah, yeah, yeah. Okay, 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 okay. I also don't remember right now. Does anybody else remember based on lecture what was the reason for doing this? Hmm. I also don't remember right now. Like you can check the transcript, right? Transcript is uploaded in the site, right? Yeah, yeah, yeah. Or sometimes you can just randomly Google. You might get lots of answers based on that, and then you can combine with the transcript and your intuition. Whatever you find on the internet, don't trust blindly. Just go through different sources and then come at a conclusion. Because in the semiconductor industry and all, you'll get hundreds and hundreds of information, and it need not be true. Yeah, that's what. So based on your intuition, notes, and the internet sources, you get your own conclusion. Yeah. So I guess that's it. Thank you for joining, everyone. And in case you have any doubts, please do drop an email. And whenever I get the textbook, I'll send it to you. Like whoever wants it. Now two people have asked. Like I'll send it to you guys. So I hope that's it. So thank you so much for joining. You may leave now. Yeah, thank you so much.